We're going to continue with directed graphs, and today talk specifically about tournaments, which is a special type of directed graph. We have three, maybe four, what are pretty easy proofs here. They're all kind of charming though. Okay, so what is a tournament? So a tournament a tournament is a digraph where every pair of vertices has exactly one arc between them. So for every UV, you either have arc U to V or V to U, and you never have the absence of an arc between two. So it kind of looks like a complete graph, okay? Where each pair of vertices has exactly one arc between them. Okay, remember, two vertices have two potential arcs between them, UV or VU. In a tournament, we have all pairs. And so in other words, another way of visualizing this, that sometimes this is used as a definition, is you start with a complete graph and you produce an orientation of it. Remember, an orientation is just choose one direction for each edge. That's the same thing as what I've described here, okay? Or it's an orientation of a complete graph. Partly to remind us of that definition. Take a complete graph, look at every edge, and orient it one way or another. Okay. All right. So, like, we can look at a few examples here. Okay, the single vertex is not too interesting as a tournament. A single edge. There's only one tournament on it with a single vertex. Yes, I could orient the reverse direction, but it's the same graph, right? Unless, again, we're talking about labeled, but we typically aren't talking about labeled for tournaments. For a triangle, so three vertices, there's two different tournaments. You can have this nice cycle, or you can have what we'll refer to later as a transitive tournament. You don't have a cycle, but you have this transitive collection of edges. So this one points here, and this one points here, and this one also points here. Okay. Those are the only two. Keep in mind, I can do other orientations, but they'll always be isomorphic to one or the other there. And then on four vertices, there's a number of different ones. And actually, that's a somewhat interesting exercise to figure out how many different orientations there are. Let me just draw one here. Say everything's like nicely oriented, like upwards like this or something. There's one orientation, okay? You can come up with many others though. Maybe let's have one with a big cycle around. Something like that, okay? There's some others on four. So these are all tournaments, right? The idea, so the notion of tournament comes from, I mean, you're playing a round robin tournament. So everyone's playing everyone, and the arrow points to the winner of that match. And so everyone has to play each other. So you do get an arrow one direction or the other. And you don't have two arrows because they don't play twice, right? You can't have a situation where A beats B and then B beats A. They just play once and there's one outcome. Yeah, good. Okay, so those are tournaments. And we're interested in finding certain objects in these tournaments. And the first one will be what's called the Hamiltonian path, which usually we talk about in general graphs, and we will later on in the class, but we can talk about it now here. Okay, so the Hamiltonian path. And remember, a path in a directed graph is directed, right? It has a direction. It's simply a spanning path. It's a path that sees every vertex of the graph. Okay, so is a path that uses all vertices of the digraph. In other words, it's a spanning path. So Hamiltonian paths are a heavily researched object in graphs. In general, we don't know everything about them that we would like to. In tournaments, we actually know quite a bit. In simple graphs, we know less, and we'll definitely talk about that later. All right. But the first theorem here is Redei's theorem. Very simple. Redei's theorem. This says that every tournament has a Hamiltonian path. As a H path. Yes, Van, very good. Yeah, so we will talk about Hamiltonian cycles in a moment here. Redei's theorem does not claim that we have a Hamiltonian cycle. So a Hamiltonian cycle is a cycle that uses every single vertex. But I mean, you can actually see already in these examples up here. This one has a Hamiltonian path and cycle, but this one only has a Hamiltonian path. It doesn't have a cycle going through everything. No. But actually, we'll prove a theorem about when does it have a Hamiltonian cycle. Okay, so the proof is very simple, and most of these today will be pretty simple, and the proofs are almost instantaneous with a picture and a little observation or two. But let's say that T is n vertex tournament, and let's just take a longest path and hopefully show that it eats up all the vertices of the graph. Okay, let P be V1, V2 up to VK be a longest path. Okay. I'll draw the picture here. So there's our longest path P, V1, V2, VK, and the edges are oriented, right? All in the same direction, like this guy here. Okay, so obviously if K equals N, then we're done. Right? That, I mean, our longest path is Hamiltonian if K equals N, all the vertices have used. So suppose there exists a U, a vertex, not on P. So there's some vertex U down here that's not on the path. Now we can collect up a few pieces of information real quick. Which arcs do we know exist here in this picture immediately, having to do with U? Anyone? Which arcs are definitely present?
Well, we know there's an arc from V1 to VU, and similarly from U to VK. Otherwise, you just tag it on. I mean, there's an arc connecting it to everything, but those cases have to be true.
Yes, exactly, right. So Van points out that U does have an arc to or from every vertex on the path, but we don't know which direction in general. But we definitely know U points to VK, simply because VK can't point to U. Otherwise, that's a longer path, right? We've seen this idea before, that edges coming out of VK in a graph have to go back in. In a digraph, they don't have to go like back in, but if there's an edge or an arc involving U and VK, it has to point to VK. And similar idea for V1, that has to point out. Sorry, not, am I getting this right? Yeah, I got this right. So from V1 has to point in to U, because if it pointed U to V1, we could extend it from that side instead. Okay. All right, so now, I like this idea a lot here. So now let's look at U and just start looking at its arcs pointing to V2, then V3, V4, V5, V6, and so on and so forth. Okay. At some point along this list here, you have to have the following situation. You have to have a change between U, pointing to U, and then pointing to V. This configuration has to occur eventually, because just look here. At first, we're pointing from U, and if V2 points, if U points to V2, then we found that configuration immediately. If not, then V2 points to U. Then look at V3. If that points to U, then keep going. If U4 points to U, keep going, keep going, keep going. But eventually, U does point to something, right? Eventually, U points to VK, and it starts off being pointed to from V1. So eventually, there's this consecutive transition here. Okay, if you don't have this picture here, then either everything points to U or U points to everything. But that obviously doesn't happen because of these endpoints here. So you have to have this flipping occur no matter what. Okay. So this flip must happen as V1U and UVK are arcs. You can make this a little more formal, it's just less fun. Like I said, you can do an induction if you want, or examine V2, examine V3, examine V4, and keep arguing that, oh, each one of those has to point to U, and then eventually you get to vk minus 1, which also points to u, and then you have this red configuration at the end. But I like the idea more that there has to be this transition at some point throughout the thing. I think it's cool. And what does this red configuration give us here? This is a longer path, right? I go from v1, I walk until I get to, say this is vi, and vi plus 1, go to u, go back to vi plus 1, end up at vk. This is a longer path. Which is a contradiction to the to maximality. So it meant this case was impossible. There was no vertex off of the path. Okay. Similar proof, we've seen this idea already. Basically, was finding a vertex connected to 2 consecutive things on a path to form a longer path. We already did this. This was just with the directed graph. You have this extra trick where there's a swapping between directions. Okay. So that's that tells us every tournament has a Hamiltonian path. As Van asked, and we pointed out, they don't necessarily have a Hamiltonian cycle. You can avoid that, but a path you can't avoid. Okay. So now it turns out that graphs, the number of Hamiltonian cycles is of some interest, and they may have few, but on average there are many. There do exist tournaments with tons of Hamiltonian paths in them. Okay, and this is Selle's theorem. Okay, so there exists an n-vertex tournament with at least n factorial over 2 to the n minus 1 Hamiltonian paths. N factorial dominates any exponential with a constant base. So as n gets large, this thing gets large here. At first, it's not much bigger, I guess, but eventually it's much, much bigger. All right. The proof of this is wonderful. This is, again, a probabilistic proof by the probabilistic method. We did one of these earlier when we found bipartite subgraphs containing half the number of edges. In a lot of ways, this one's an even easier argument and really should be the first time you ever see this method. But we typically don't start graph theory with digraphs and Hamiltonian paths and stuff. But this is an absolute beauty. In fact, this probabilistic proof predates the method, right? This was already written down in the literature using this technique, and it was later realized that, oh wait, this is actually predates like this method being introduced as a general technique. Okay, so this is by via probabilistic method. Okay, and so what's the idea in a probabilistic method? We're going to create some probability space and then show there's an object in that, and the members of the probability space are tournaments. And we're going to show that we're going to look at the expectation of the number of Hamiltonian paths in a random tournament. And we're going to show that expectation is at least this quantity here. And that means, and the expectation is the average. So it means on average, tournaments have this many Hamiltonian paths. If this is the average number of Hamiltonian paths in a tournament, then there exists some tournament with at least this many, right? They can't all manage to be below the average, otherwise that's not the average, okay? So it's just an averaging argument as well, but we can use probability to set it up very nicely. I'll mention again as an advertisement, I teach a topics course next semester on the probabilistic method, where we'll use this technique to prove things in graph theory. Some of these things we'll see a second time, of course, but we'll prove things about all different combinatorics disciplines. So if you guys are interested in that, that'll be the focus of that course there. Okay. All right. So the probability space here is going to be all the n-vertex tournaments. So I want to select an n-vertex tournament at random. Okay. So you can just imagine for a second, there's only so many of those. Like, how do you actually select one at random? Actually, the nice thing here is we can go back to the orientation question about directed graphs. Here we're going to actually think of them as being labeled when we solve the problem here. But the issue of labeled versus not labeled will not change the average here, okay, as you see from the argument here. And so we'll show the existence of a labeled n-vertex tournament with at least this many Hamiltonian paths, but then we can just ignore the labels, and then we found one with, that was unlabeled. Like, of course, if a labeled one exists, then an ordinary one exists. Okay, so the cool thing here is, yes, we could say, oh, just imagine all the tournaments and just choose one at random. But like, how do you know what that looks like? And how do you do any computations about what's the likelihood of having Hamiltonian path and so on? So can anyone suggest to me a way of actually producing a random one? Like say I literally told you, you have 100 vertices to work with, draw me a random tournament on those 100 vertices. What would you like literally try to do to create one? What's a reasonable approach? Anybody have an idea? Yeah. Van is a great suggestion there in the chat. Look at a pair of vertices. There's two potential arcs. Flip a coin. Choose left to right or right to left based on the coin flip. That'll orient each one of your edges, and that produces a tournament. And that's a reasonable, actually uniform operation as well, right? I mean, if you think about it a little bit, every tournament that you can produce will have the same probability of occurring in that thing there, okay? All right, so what did I say here? Yeah, okay, so orient, so let us randomly orient the edges of Kn to produce a tournament. Okay. Well, we don't need to compute the probability of any one tournament occurring, but it's not that hard to figure out. It's just going to be 1/2 raised to the n choose 2. Right? There's n choose 2 coin flips that you're going to make, one for each pair of vertices, and you get either orientation with probability 1/2. This again is for labeled. If they're unlabeled, then you have to divide out by isomorphism classes, and this is not easy to solve. In fact, I don't even know if it has a simple solution here. But if we keep it labeled, each one has probability this, okay? But that's not part of the problem, so I'm just going to erase that. We don't actually need to know the probability of any one occurring. We just need to compute some random variables. Okay, so let x be the random variable counting the number of Hamiltonian paths in our random tournament. Okay, so you produce a random tournament, you go through and check how many Hamiltonian paths are there in there. You can say do a brute force algorithm to do that. I mean, you don't have to do it. Each one has a certain amount. X records that quantity for a given one. Okay. All right. So now, and this is very common in probabilistic proofs, I would like to break this X down into indicator variables so that I can apply linearity of expectation. Okay. If you haven't had a probability course here and you don't know what that is, that's okay. I'm not going to ask about this in a homework necessarily. But anyway, so let's introduce indicator random variables xi for each of the n factorial potential Hamiltonian paths. Okay, and I'll add something in a second here. So what do I mean by indicator variable? So an indicator variable, okay, so first of all, think for a second that, you know, here's a graph here, and here's a potential Hamiltonian path, right? Here's a path in the thing that might, you know, like it's a set of vertices in order here that might be a path or not. So for this guy, say this is the 300th one in my listing of potential Hamiltonian paths. This xi simply records a 1 if this thing indeed appears in my tournament, and it records a 0 otherwise. Okay, that's all the indicator variable does. It keeps track of one specific Hamiltonian path. Okay, there are n factorial Hamiltonian paths potentially in my graph. Where's n factorial come from? Why are there this many like candidate Hamiltonian paths? There's one for each ordering of the vertices of my graph. So say n equals 4 for a second here, and I've got 4 vertices. If I lay them out 1, 2, 3, 4, that's potentially a Hamiltonian path. 1 to 2 to 3 to 4, but also 2 to 3 to 4 to 1 is a potential one. That's another ordering of the vertices. So anyway, I shuffle up the vertices. That tells us, oh, that might be a Hamiltonian path by going in that very specific order. Again, that relies very much on the vertices being labeled, right? Anyway, so I grab the vertices. So let me just put this 1 for each ordering of the vertices of the tournament T. Okay. So anyway, you order those, there's a candidate Hamiltonian path. And then it's just a little bit of computation here. Why is that written there? Oh, yeah, okay. So we do need to calculate one thing here. So indicator variable equals 1 or 0. In a moment, the reason we like to transform to indicator variables is because if I want to know the expectation of an indicator variable xi, it's just simply the probability that xi equals 1. Okay, expectation, I mean, I don't want to go through the full details, but the expectation, so, I mean, what's the expectation of a random variable? Sorry. Expectation of a random variable. Okay, I should say x, that's a specific one here. It's just a sum over all, oh man, I don't want to do this, but you can write probability that y equals, say it's a discrete random variable times I. So you just compute this sum. You take the probability that y equals I times the value I. You just compute these over every potential value that y can take on for a random variable. But when y is an indicator variable and only has values 1 and 0, then this sum is over I equals 1 and 0, and the 0 term vanishes because 0 times anything is 0, and I'm only looking at probability that y equals 1. Okay, so the expectation of xi is equal to the probability that xi equals 1. Okay, that's true in general. That's why we like to introduce these guys, because then, let me just put the expectation of xi equals the probability that xi equals 1, which is just the probability that that specific ordering of vertices has a Hamiltonian path on it. Okay, so given ordering has a Hamiltonian path. And we can actually compute that real quick. So say I give you a set of vertices and ask, does this form a Hamiltonian path in this order? How would it form a Hamiltonian path? Like, let's say I go along here and I had a coin flip for each of these things here. In order to get a Hamiltonian path here, what had to happen? Yeah, exactly, Dakota. I had to just keep getting, exactly, or Eric, we have to win the flip n-1 times. Yeah, that's interesting. I have something slightly different written in my notes here. It's a little troubling. Okay, so I'd have to win the flip like this n-1 times, right, and go in this direction. Yeah, okay, it's fine. I know what the mistake I made was, but if I just don't say anything about it, then we'll be fine. I have to change something in the notes here. So I have to win the flip n-1 times. Okay, that'll give me the probability that. What I've written in the notes was you'd have to win the flip n times, which is wrong. Eric's absolutely right. It's n-1 times. And then there's two potential directions here to have a Hamiltonian path. But since we're talking about an ordered set of vertices, if everything was oriented this way, these vertices, while they do have a Hamiltonian path on them, it's not the one according to this orientation. That'd be a different ordering. Yeah, so it's this guy here. So need to win, I like that, flip n-1 times, right? If I put the vertices here, in order for to have a Hamiltonian path on them, I need to be oriented left to right every single time. Otherwise, I don't get what I want. Okay, and now the end of the proof is just a computation here. As I warned you, we need to know the expectation of x, the total number of Hamiltonian paths, because if we know that, we know there exists one of the objects in my probability space that beats x, or is at least as large as x. Okay, so the expectation of x is the expectation of all the indicator variables. I equals 1 up to n factorial. Okay, right? This is linearity of expectation. The x can be written as the sum of the xi's, right? Let's just go up here for a second here. X is the random variable counting the number of Hamiltonian paths, and each xi gives me a 1 or a 0 for each individual Hamiltonian path. So if I want to know how many I have, I just check each one individually and add a 1 to my running total if that's a Hamiltonian path, and add 0 otherwise. So x equals the sum of the xi's. I should have put that here. So x equals the sum of the xi's. And it looks a little bit weird, but this sum goes from I equals 1 up to n factorial. There's n factorial of these indicator variables, right? 1 for each potential Hamiltonian path. Then we pointed out that the expectation of an indicator variable xi is simply the probability that xi equals 1. And we computed the probability that xi equals 1, right? That was this quantity here, 1 over 2 to the n minus 1. So then, then I'll just write out the solution here. We have 2 to the n minus 1 with n factorial on top. Each of these terms inside of here is 1 over 2 to the n minus 1, and there's n factorial terms in the sum, all of which are identical. So the answer is this thing here, okay? And that's basically the end of the proof, right? Because this means that, so there exists a tournament with at least the expectation of x many Hamiltonian paths. I mean, that doesn't follow from this. That's always true, right? As we pointed out, there exists a tournament who has at least as many as the average number of Hamiltonian paths. And this thing here equals n factorial over 2 to the n minus 1. So on averages, we have this many, therefore there's one that beats it. And that's the end of the proof, okay? Again, like in most probabilistic proofs, we never constructed this thing. We didn't find how to orient it. We didn't do anything of the sort. Like if you wanted to find one, it might be hard. Of course, an idea you might try is flip a coin and then check. And you on average, you have at least this many, or you have this many. So it seems reasonable that after a few tries, we're going to beat it, right? Sometimes that works great. Other times it doesn't work great. It kind of depends on how things are set up. Okay, so yeah, that's one of my favorites. Let's now try to look for a Hamiltonian cycle. Okay, so let me write out what that is, although I think it's pretty evident now, having looked at what we have. A Hamiltonian cycle is a spanning cycle. It's a cycle that uses every single vertex. And actually, if we write it this way, it's nice, because then this definition works just fine for digraphs or for graphs, right? We know a cycle in a digraph is going to be directed automatically, and in an ordinary graph, it's just a cycle's a cycle. There's no orientation. So Hamiltonian cycles, one uses each vertex. Okay. We'll talk about it later, but this is related to like, a traveling salesman type problem. I want to visit every city without backtracking. That would produce a Hamiltonian cycle and where I started. Okay, so this is Camion theorem. And this tells us exactly when we have a Hamiltonian cycle in a digraph. Okay, so a tournament T has a Hamiltonian cycle if and only if T is strongly connected. Okay, that's it. So having a Hamiltonian cycle is equivalent to being strongly connected. Last time we defined and proved when a graph is strongly connected. We defined strongly connected. We talked about a strongly connected orientation, which is closely related. But strongly connected means for every pair of vertices, there's a way to get from A to B and from B to A. So you have directed paths in both directions. That doesn't necessarily imply immediately that they're on a directed cycle together, right? Because like those paths could use vertices from each other. In fact, I mean, they could even look identical. Like literally, you could go one direction and back. Not in a tournament, but like in an ordinary digraph. Okay, so nonetheless, in a tournament, you have a Hamiltonian cycle if and only if you're strongly connected. We've seen that you don't always have a Hamiltonian cycle, right? We saw this like very simple triangle here. This guy here. Okay, this works just fine. This is a legitimate tournament here. This does not have a Hamiltonian cycle, right? There's no way of passing around the three, but it also is not strongly connected, right? Because this vertex, for instance, will not be able to reach the others starting there. Like it's kind of isolated in a sense, right? We can't get out. Okay. All right. The proof of this resembles Redei's theorem. We're going to take a largest cycle and then show that we can enlarge it and eventually cover everything. Okay. So first, let's just do the forward direction here. And so if we have a Hamiltonian cycle, then we're strongly connected. This is obvious, right? If I have a cycle that includes every single vertex of the graph, then if I grab two vertices on that cycle, in fact, we've already seen this, there's obviously paths between the two in both directions. Go this way and then go this way. Like that's not only are there two, they're even disjoint from each other. It's like really nice. and I can take any two vertices. So that immediately works. So that part's not the interesting part of the proof. It's the reverse direction, that you tell me T is strongly connected. How do I find my Hamiltonian cycle? Okay, so suppose T is strongly connected, and then want to find a Hamiltonian cycle. Jeez. Okay. All right, so let C be a longest cycle in T. Here's C. And again, it's directed, because that's what cycle means in a digraph. Okay, so we draw this. There's an immediate question to be asked, right? Whenever we talk about a longest substructure, what's the first thing you have to clarify?
Show that any of them exist.
Yeah, is there even a cycle at all? So does a cycle exist? I'm not going to answer this immediately. I'm going to let you think about this a little bit, but it follows immediately from the strongly connected condition. Now, I said if you take two vertices that have paths in both directions, it doesn't mean those two paths are vertex disjoint. You know, it doesn't mean they look like this and form a cycle. But from those two alone, you can guarantee the existence of a directed cycle. Okay? Yes, via strongly connected. Okay? It's not that hard to show that you at least have a nice little triangle or potentially something longer. Okay? But I'll leave that like as an exercise, I guess. Okay. Okay, so again, if, did we name the vertices? We don't really need to. So if C spans T, then we're done. Same thing as before. If the longest cycle is a Hamiltonian cycle, then we have what we want. We don't have to think anymore. Okay? So what we'll look at is a vertex U that's off of the cycle. Okay? So let U be a vertex not on C. Okay, so now let's look at the edges from U to C real quick, the arcs, right? So this is a tournament. So for every vertex on here and U, there is an arc in one direction or the other, okay? Now, let's suppose for a second, U pointed to some vertex like that, and the vertex later pointed to U. Say we had this picture here, okay? In Redei's theorem, we noticed that if we had two of these on the ends, then there would be this like transition happening. Same thing happens here. If U points to a vertex and there's a different vertex that points to U, then actually at some point we can find the following, where we have two consecutive ones that swap like this, okay? Like again, as soon as U points to this one, you can check one after another that they all have to keep pointing from U to this, otherwise you get this picture, okay? So if there exists X and Y on C such that X, U, and U, Y are arcs, then exists consecutive, I don't know, AB with same property. Okay, so if there's a vertex that points, an edge that points away from you and an edge that points to you, then we can actually guarantee that there's two such like that that are consecutive on the cycle, okay, that form this thing here. Now, if we have that, what does that mean? What if, you know, now I have an A and B that are consecutive on the cycle, and A points to U and U points to B? Then we have a longer cycle, right? This forms a longer cycle, which would be a contradiction to the length of the cycle. Unlike in Redei's theorem, this is not the end of the proof, right? What does this tell us about U then? This doesn't actually end the proof, right? This is if we had two arcs with opposite directions according to U. So we're still allowed to have a U. It's just if U exists, all of its vertices point to the cycle, all of its arcs point to the cycle, or all the arcs point to U, one or the other. We just don't have a mix. So this means, so we have the following picture. Here's my cycle, C, and here's a vertex U that's outside of it. Either everything out of U points to the cycle or the reverse, okay? So I'm gonna erase this immediately because I wanna say something else then. So either all arcs go from U to C or vice versa. And this holds for any vertex that's not on C, right? Any vertex either points everything to C or has everything pointing to C. And so what I'm going to do with the remaining vertices, I'm going to call this set out and this set in. These are the vertices who send all their arcs directed towards C. If this set is non-empty, and in is everything like this. Here's my picture. Now, we proved that at least one of these two sets is non-empty. I mean, we didn't prove it. We're assuming that, right? Otherwise, C eats up every single vertex. So there might be some vertices in out, and there might be some vertices in. And we'll establish in just a moment that the two are non-empty. Okay, so actually, let's do that now. Well, we do something simultaneous here. Let's just suppose for a second there are vertices in both of these, at least one in both. We know there's one vertex in the union of the two of those because it's vertices outside. And we know that every vertex outside either sends everything to C or has everything from C sending to it. That was what we established up here. Now, what about edges between these two classes? What about arcs involving these two classes? Let's use the strongly connected property to say something about arcs between those two. Let's think about strongly connectedness for a second and look at vertices in out. Forget in for a second. Vertices from out, they can reach C, certainly, and they can reach in, certainly. So if I have a vertex here, I can reach anything in here and anything over here. What can I not reach, though? Well, actually, it's not clear what I can't reach. Starting from here, it seems that I could, in principle, can reach everything. But what is the problem here for strongly connectedness?
Vertices in C and in the inset can't reach the outset.
Yeah, good, Brad. There's no way to get to the outset. This outset's like isolated by this wall pointing to C here. So in order to make the vertices of outset accessible, the arcs have to go this direction here. Or at least there's got to exist one arc, right? Maybe one is enough, but there's definitely got to be an arc from in to out. There exists an in to out arc. Otherwise, I'm going to call this like U. Otherwise, there doesn't exist, say, like AU paths in T, right? If this edge doesn't exist, then there's no possible way to get to U ever, starting from somewhere else, okay? But now, look at this picture. Now this picture, we actually have a longer cycle somehow, right? There's an end vertex here, an end vertex here. This thing goes here to every single, there's every single arc is available from out to C, and similarly from in, from C to in. So I can take that one, and say these two are consecutive. Now the longer cycle, actually it's longer by 2, okay? This is a longer cycle, okay, which is a contradiction. Now, there is one hanging question here is, what if like one of out or in is empty, right? Like that, like I kind of assumed there were vertices in out and in, but actually I didn't, right? I actually established it. I proved that this red edge has to exist. This red arc has to exist. If the red arc has to exist, what does this tell me about the sizes of out and in? Can they be empty? No, I mean, if there's an arc between two sets, then those two sets had vertices in them in the first place. If in was empty, then there's no possible way to have this red arc, but you have to have this red arc. Otherwise, U, for instance, is not available, okay? And that's the end of the proof, right? We just found a longer cycle. But it wasn't quite as easy as Redei's theorem, where we just had a vertex off and said, oh, great, we can extend the path. This one, we had to extend it by a cycle. And so it wasn't enough. Like, we don't know that U had this alternating thing. In fact, we ruled that out. Okay. All right, so that ends that proof there. All right, and then one more thing about tournaments here. I already alluded to this, but there's a special type of tournament called a transitive tournament. Okay. So definition, a tournament is transitive if, I mean, it just has this transitive property, if when x, y, and y, z are arcs, then so is x, z. Right? This is just our ordinary transitive property in terms of arcs in a graph, but this is a transitive property you might see in algebra or in arithmetic, anything like this. If x, y, so if we can go from x to y and y to z, then we should also be able to go from x to z. Okay, so if I look at 3 vertices, x, y, and z, x, y, z, then whenever x points to y and y points to z, I should be able to take the shortcut x to z. Right? That's clearly like the transitive property of mathematics, right? That we see right here. So if that property holds for, I mean, and that means for all triples of vertices in my tournament, if this is always holding, then the tournament is called transitive. Okay. Why is this thing desirable? Well, it's desirable because when you talk about a round robin tournament, the ideal situation is that the result of the matches is transitive, right? If you watch football and the season ends and there's a team that's, lost 1 game, and then you look at the team that beat them and like you say, oh, but this team beat this team, beat this team, and you have this like circle. And so you never know who's the best because there was like no one that beat everyone, unless you never lost, right? But you have these situations that are undesirable. It's like, how do you say you're the champion if someone beat you and the someone who beat that guy, you beat? Like, then you have this like circle, right? But in a transitive tournament, it's like if I beat A and A beat B, then I also must have beaten B, right? That's the situation we hope for, which basically never happens, but that's a transitive property. So those are tournaments we're very interested in. And we have this nice theorem that characterizes transitive tournaments. So tournaments transitive is equivalent to a bunch of different things here. Okay. And I'm not going to prove, maybe we'll just prove the first one. The rest of these are going to be exercises. These are classic exercises. Okay, so the following, okay, so yeah, I mean, so just keep in mind, this is for any 3 vertices, x, y, z, right? If x, y is an edge arc and y, z is an arc, then x, z should also be an arc. So this is transitive, but like, for instance, this, this triple here is not transitive, right? I have this cycle. This is not transitive. This guy beats this guy, beats this guy, beats this guy, right? It's no transitive property. So not transitive. Okay, so the following are equivalent for a tournament T on at least 2 vertices. Maybe I'll prove the first one. We have a minute or 2. So this is our transitive tournament characterization theorem. So number 1, T is transitive. Okay. Good. First is that T has no cycles. If you're transitive, then you can't have a directed cycle at all. That's pretty easy to see. Okay. Actually, you can modify this slightly. You can weaken it. The 2 are equivalent to each other, but T has no cycles of length 3. Okay. So this just seems like a weakening of the previous, but the point is, in a tournament, these 2 are equivalent. Having no cycles and having no cycles of length 3 are actually equivalent to one another. That doesn't seem immediately obvious, so it's not that hard to see though. 4, T has out degrees 0, 1, 2, up to n-1. So all the out degrees are distinct in a transitive tournament. This again gives you a very nice ranking of the vertices, right? You can rank vertices now by their out degree. Say you point to the team that beats you You can do either one. It means that the team with no edges going out never lost. And another team lost 1, lost 2, lost 3, lost 4, lost n-1. Very natural way to decide who's the best and who's the worst in that tournament. Okay. And then one interesting one here, oops, 5, is that T has exactly one Hamiltonian path. Okay, that's pretty interesting too. If you have exactly one Hamiltonian path, that also suggests a way of making a ranking, right? You have this one Hamiltonian path. The end of the path might be the champion, and the beginning of the path might be the worst loser. This is also interesting because what we saw in Selle's theorem, that on average you have tons of Hamiltonian paths in a tournament, right? But this one has, there do exist those with exactly one. Transitive tournaments have exactly one Hamiltonian path. They don't have a Hamiltonian cycle, obviously, right? Because they don't have any cycles at all. Okay, there's actually a few other ones that you can make equivalent as well here. You can talk about posets, and there's all kinds of other cool stuff going on. But maybe let me just sketch why 1 implies 2. Okay, it's very simple here. So say there exists a cycle, V1, V2, up to VK, and then V1 again. Right, so here's my cycle. I'm going to draw it like this. I've got all the edges directed this way, and then 1 going back. So there's my cycle, right? This one goes here too. So let's prove that this is not, that like transitivity causes a contradiction here, okay? So what can I say about the edge between these two vertices? The arc involving these two vertices? Yeah, transitivity says it's got to go forward as well, right? Because this one plus this one implies that one goes forward as well. And now what about this vertex to this vertex? Well, it's concatenation of this edge and this edge. So this one's got to be forward oriented as well. And they've got to keep being forward oriented by just repeatedly applying transitivity. And then the interesting one is this last one, from V1 to the end of the cycle, VK. This has also got to be forward oriented. But we already have the reverse oriented edge there. So this says that we have two arcs between two vertices. So V1, VK, oops, and VK, V1 are arcs. But that contradicts the property of being a tournament, for instance. Tournaments have exactly one arc between two. Okay. So that's the proof of that. That implies 1 implies 2. That 2 implies 3 and so on and back to 1. That'll be a homework on the next homework set, which I'll probably assign on Wednesday. Anyway, so that'll do it for today.